Yeah, thanks for having me. Yeah, you see it fine?
We're getting the presenter
mode. Sorry. Sharing the wrong.
Yeah, we already get it right this time.
Sharing the wrong desktop, I think. Now, no.
Yeah, no, it's good.
Now it's good. Okay. Thanks. So yeah, thank you all for being here, and thanks for having me. So as Ben said, I'm going to talk about strong lensing and how to combine simulations and observation to use strong gravitational lensing to say something about the nature of dark matter, and so how to distinguish cold dark matter from alternative model like warm dark matter or self-interacting dark matter. So what I do is something that I like to describe in between theory and observation. So theoretical model of structure formation are something that from equations, from first principle and distribution of the matter in the universe tells us what is the distribution of dark matter. But these are analytical models that cannot really be solved effectively in time and redshift to have predictions. On the other hand, there are observational data. And so in this specific case, there's strong lensing images like these beautiful arcs here. And so one can combine the two by looking at simulations. This is just an advertisement of what I do. So computational simulations that then connect the two aspects. And this is fundamental in particular for dark matter, because we can simulate now the evolution of structures with different dark matter models. And recently, thanks to this amazing advancement in simulations, also generate realistic galaxies and look at the population that produced by simulation and compared to the observations. So dark matter is one of the still most striking of open questions in astrophysics. And then, so in the standard model of structure formation, we think that dark matter is the majority of matter in the universe. And so it shapes the formation of structures in time. So as seen here by simulations, structures appear and form the cosmic web. So there's always some debate of whether dark matter is actually real, which is fair enough, because we haven't detected the particles yet, so we don't know what it is. On the other hand, there's plenty of observational evidence that tells us that our model is not too bad, so it can produce and predict observables. And so even far from what I directly do, so there's strong lensing, one beautiful thing is the cosmic web. So it's this filamentary distribution of matter in the universe that is produced by simulation, but is also reproduced by observations. And so while here on the top, there's dark matter only simulations, then you have a distribution of galaxies in the Vipers survey, in the SDSS survey, and the distribution of gas on the line of sight traced by the Lyman alpha forest. And all these look very similar, so this gives us a hint that dark matter should be real. If it's not real, then something else must cause the same effect. In any case, so the standard model tells us that dark matter is cold. However, while on large scales, everything works quite well with this model, there's a series of inconsistencies between the prediction from simulations and small scales, the results. And so this has produced a series of different alternative models. And the two that I'm talking about today are warm and self-interacting dark matter. They both originated from these small scale controversies, like the missing satellites problem, the too big to fail problem, the core cusp problem. So the failure of cold dark matter simulations to reproduce, for example, the number of satellites in the Milky Way, even though this has been partially solved now by the inclusion of baryons, the fact that not all observed galaxies seems to have a central cusp, but some seem to have a core. So these models were motivated by small scale problems in terms of satellites in particular. So warm dark matter, it's a model that is conceptually similar to cold dark matter, but the particles are so they still interact only with gravity, but they're lighter, so they're the scale of the kilo electron volt instead of the giga electron volt. So they're faster, and then their movement destroys some of the small scale perturbation. It means that small halos will not form, while they will form in CDM, given the same initial conditions. On the other hand, self-interacting dark matter uses different models where particles interact not only gravitation, but also through strong interactions. And so there is energy and momentum that can be exchanged between the particles and affect the shape of halos and galaxies and so on, as will become clear later. So just to say, these are two models that are useful at the moment to be tested with lensing, but these are only two of a huge range of alternative models that are being explored by different groups and different techniques and so on. So this is a nice scheme of all the possibilities, and then I will only cover some specific cases. So from the simulation point of view, this is how warmer and self-interacting dark matter simulations look like. So as I said, on large scales, everything looks pretty much the same as CDM. You have this cosmic web, you have filaments and halos for the main galaxies. But on small scales, that's where you see the difference. On the left, it's two simulations of the same halo, which is, I think here, Milky Way size halos. And in the top is the CDM, and the bottom is warm dark matter. It's a particularly warm dark matter. So, but the clear difference is that in warm dark matter, these small scale substructure are erased. And so you're left with only the brightest peaks, which in this case, just the more massive ones, which, for example, in the Milky Way will be the host of the main Milky Way satellites. So the question is whether or not all these other small dark clumps actually exist or not. On the right, there's also the difference between CDM and some SIDM simulations, so self-interacting dark matter. So they produce a similar effect. Some models also reduce the number of substructure, but the main effect of self-interacting dark matter is to smooth out the central density of halos because of these interactions in the highest density regions. So from the lensing point of view, these two things can be measured in different ways. So you can look at two different aspects. So from the warm dark matter point of view, what we do is to look at the very small scales and try to measure the halo and subhalo mass function, which is the plot shown here, so that the number density of predicted number density of small mass halo. In CDM, you see there's an infinite number of small masses, while in warmer and warmer model, there's this cutoff. And so we try to look at a very small scales to measure this mass function and compare it with simulation. In self-interacting dark matter instead, what we do is to try to measure the profile of the main halo, so the profile of the main galaxy that acts as a lens. So I will go through these two effects, more about the first because we have done a lot more work on it, and the self-interacting part is still ongoing. But so in general, so strong lensing is this effect for which the shape of a background source, which can be a galaxy or a quasar, is deflected by this mass in between, so a galaxy or a cluster. And all the cases that I'm going to show here are galaxy-galaxy lensing, so where the source and the background, so the source and the lens are both galaxies. So in this case, you get extended arcs. So here on the bottom right, you can see the arc is generated by the deflection of the background galaxies, while the other pictures show a quasar. So if the source is a point as a quasar, instead of a extended arc, what you get is multiple images of the same thing. So how can this be used to say something about dark matter? So in the case of arcs, which is what I mainly work on, you have the main lens, but then we saw that in simulation, there's all these small clamps. So if they fall on top on the arc that's generated, so if the small clamps inside the halos or along the line of sight are in the right position, they can be a secondary lens, a small mass lens that can introduce extra deflections. And here on the left, you can see examples of what would happen for a very, very idealized case. So for a thin arc, if you put a 10 to the 6 and 10 to the 7 or 10 to the 8 solar masses, dark halo on top of it, so an NFW profile right on top of it, you get a deflection that's bigger with mass. And modeling this, one can measure the mass, and ideally, if we had many of these, we could measure the mass function. So from here, it seems very trivial, but the problem is data mostly don't look like these really nice arcs. They mostly look like this. So this is a mock image for that kind of reproduce the properties and the resolution of HST data. And so in these three images, the left one is generated by having only the main halo as a lens. So here it's a lens model from a real system where the central galaxy has been subtracted. So this is why you only see the lensed arc. So in the first one, it's only the smooth model. And then the second and the third one, there is a substructure in the lens added to the model that creates a perturbation. The point is, by looking at this, you can't really see, you couldn't really determine where the substructure is, maybe in the central case, but only by comparison. So these are the location of the actual extra perturbation. And the only way to detect this is by looking at differences between the smooth model and the perturbed model. So this is how the observational technique looks in practice. So this is something that's called gravitational imaging, and it's a technique that has been invented by Simona Vegetti and Leon Koopmans. And so it's in practice a series of code where you get the lensed image, which is here on the left is an example from Keck adaptive optic data. Then you model the mass of the main lensing with a singularity terminal ellipsoidal sphere. You get the best model, the residuals, and then you're able to reconstruct how the lens galaxy looks like. So how the source looks like. Of course, then it doesn't really look exactly like a galaxy because of resolution, PSF effects, etc. But then to look at substructure, what we do is then we scan the plane of the image by adding extra density correction, so clumpy distribution of mass on top of it, and we see if there is one case where this is favored. So the model that has the smooth model and the perturbation is actually favored compared to the model with the smooth component alone. And this results in something like here in the density correction plot. So this is a localized excess in mass that is not predicted by the main model. And if there is no light associated with it, up to the limit of the image that we have, then it can be interpreted as a small dark matter halo, so a substructure, or a halo along the line of sight. And so the idea of this entire business is then we get all these images, we try to find substructure, we find them, we don't find them, we get a statistic, we compare it with simulations, and then we can say something about which dark matter model we think it's real. And then the prediction can be compared with those that come from other techniques. So how simulation come into play here is that, so in the past we had mostly dark matter only simulations, which led to all the inconsistencies with observation. But now there's many, so these are just two examples that are also kind of old by now, but these are two examples of big runs, including hydrodynamical treatment of gas and stars and metals and so on. So we use large-scale simulations like the illustrious or Eagle, the illustrious CNG, to select analogs of the lens galaxies. So we search for, in this case, our early type galaxies or elliptical galaxies, a ratio between 0.2 and 1, which are the typical lenses that we have. And then from this population, we can compare them to the observed cases. So here on the left, you have distribution of illustrious and Eagle galaxies in stellar mass as a function of effective radius compared to some data. So the lax lenses are a sample of lenses that are 0.2. And so we try to select those that are very similar to the observed galaxies. And then these are re-simulated again a higher resolution, and then they're resimulated in different dark matter models, because it would be nice to have a large scale run with different models and all the full treatment of hydrodynamics, but this simulation take months and months to run. So this is not computationally feasible, while just looking at one halo at higher resolution is way more efficient. So what this results then is, then we have these boxes. So here on the top, it is a halo. In this case, it's a 10 to the 13 solar masses, an elliptical, hosting an elliptical galaxy. On the top, you see a distribution of dark matter in CDM and into warmer dark matter model. They get warmer and warmer by going to the right. So you see there's fewer small dots, so fewer substructures. Then in practice, the lensing signal comes from a very, very small area at the center, which describes why these measurements in observations are very tricky. So while the first row of plots is in a box of 2 megaparsec, you see that already by looking at a central part of like 200 kiloparsec, which is more or less half of the virial radius, fine, we can see that there is difference in the number of substructure, but it still starts to be a small number statistics. And then actually the lens images, these are mock, to look like, again, HST observations come from a very, very small area at the center. And so this is why we need a lot of observation and a lot of simulations and a lot of careful analysis for this. So in practice, once we have this simulation, we use them to calculate what is the expected number of perturbations that we try to detect then in the observations. And so for this, we use the central halo, so all the substructure in the central halo. But then, since lensing is something that happens between us, so the observer and the lens and the source, there's a lot of space in between. There's hundreds and hundreds of megaparsec square, which are also populated by dark matter halos. So in practice, one has to look at the entire distribution of structures along the line of sight and count all the small halos that can generate perturbations in this case. So here, we're not looking at a extended structure. We're excluding everything that has a luminous galaxy. We're just trying to focus on masses below, let's say, 10 to the 10 solar masses. And so it's important to consider the entire distribution of structure, because here on the left is what you would have only in looking at the density of substructure in the halos in a 50 by 50 arcsecond plane next to the center of the halo. And then on the right is what actually needs to be considered by looking at the entire line of sight. So once we have these predictions, then we compare them to data. So in practice, depending on the instrument, the resolution of the instruments determines which are the perturbations that we're able to detect. So clearly, big halos generate bigger deflections. Small halos generate smaller deflections, and so to go down in halo mass, we need higher and higher resolution observations. So, for example, this is an HST image of a lens galaxy at redshift 0.9, and the range of masses that we're able to detect at the HST resolution is around 10 to the 9 solar masses. And you can see that this is not very interesting, because in this range of masses, most of CDM and alternative warm dark matter models predict more or less the same number of halos. So then we need to go to lower masses. So this can be done, for example, with adaptive optics. This is the same galaxy observed with Keck. So the resolution goes down by a factor of more or less 2, and we are able to go down to 10 to the 8. Then I don't have images for this, but theoretically, some of the ALMA lenses will be able to cover even a slightly lower range in mass. And you see that now here we start to be in a regime where the differences between CDM and alternative models can be even order of magnitude. And so at this point, if we detect one very small halo, then this could already be a challenge for alternative models. Or if we detect nothing, this is definitely a challenge for CDM. But I have to say that then the final gray hope for this field is radio. And so in particular, the VLBI images that the group in Munich is currently analyzing. Here, this is again the same. This is the same galaxies, but this is an image of the radio jet of the source instead of the optical component. And I will have like a picture of the source later. And you see that at this frequency and with this analysis, the arc actually looks like a line. And so it really looks like the idealized example that I had at the beginning. So this is super promising, because if there was perturbation on top of the arc, this would be almost visible by eye. And then from the optical point of view, of course, there's the ALT, which in theory should reach a resolution similar to this, but for now we only have MOX, so we can only make prediction. Of course, then one of the technical difficulties of this analysis is then the higher resolution you have, the more pixels you have, the bigger your data are. So it takes longer and longer to analyze the data. So as a final remark is that then now we have these predictions, we have these images of how actually the connection is done. So in some cases, in the data, there is actually a detection. So, but these are very few. So in the samples that we have so far, for instance, in HSC and Keck, there have been in ALMA, there have been only 3 claimed detection, one in ALMA, one in Keck, I think, and one in HSC data by the group in Munich and by different groups. So these are clearly not frequent events, both due to the resolution and both to the fact that we're looking at small scales and the measurements are very tricky. So in most cases, what we are dealing with is not clear detections, but it's uncertainties and non-detection. So how we take this into account? So the idea is that we need to know for each lens, not only if we detected something or not, but what is that we expect to detect given this theory. And so this is done through something that we call sensitivity maps. It will be important for all the next plots. So here on the left is an HSC image of a galaxy Rashi 0.7. So you see here the central galaxy, and you see the lensed arc. That's a source of Rashi 2.5, I think. And then on the right, you see a color map, which is called sensitivity map. So each pixel here, the color shows what is the minimum detectable mass that you can detect with this image. So the labels of the color bar are a bit small, I apologize. But so the key here is that we scan the plane, we add this NFW perturbation at each pixel, and then compute the model, compute the evidence, the Bayesian evidence of the model, and compare this with the smooth model. So even we know that we do this by hand, so we know it's not a real detection, but we test by how much an extra perturbation would change our data. And so if we would be able to detect this given the surface brightening distribution of the arc, because you have to imagine that. So this is all based on the fact that the pixels in the surface brightness distribution of the arc are not what you expect given a smooth model. So if the source, for example, all has the same color, this is equivalent to if you look at a wall and you have tiles of all the same color. If you reshuffle them, then you can't see anything. However, if the source in this case or the tiles are of different colors and then you reshuffle them, it's easier to see. So lenses observed with the same instrument at the same resolution not all have the same sensitivity map, because in some cases the structure of the source guarantees a higher sensitivity. So in this map, the darkest points are where you can detect lower mass halos. So you can see they are concentrated around the brightest points in the arc, where the gradient to the surface brightness distribution is the best. And we do this for every lens to take into account detection and non-detection. So the current constraints that we have are summarized in this paper by one PhD student in Munich that combined constraints from gravitational imaging and other probes. So here, every row, it's a different method. The first two are lensing. So low redshift lenses, which here on the right are the SLACs lenses, so around redshift 0.2. Then the Bell's lenses, the redshift 0.5. Then you have constraints on the left coming from the Lyman alpha forest, so the distribution of neutral hydrogen along the line of sight, and the number of Milky Way satellites. And so there's many axes here, but what you should look at is the top axis, which shows what the mass of the warm dark matter particle is, and these are posteriors. So it's in log, but so CDM is all the way to the left, and the more you go to the right, the warmer and warmer models you are considering. So the first thing we see here is that the Lyman alpha forest constraint and the Milky Way satellites are more stringent than the lensing ones, and so they dominate the joint constraints. So the idea now that we had is how to improve this. What is the observational strategies that we need to get more lenses, better lenses, higher resolution? What would actually allow us to reach the same level of constraining power of the other models? And so this is what we've been doing with mock data. So this is an example of the same. So it is the same lens model from the HST system that I showed before, and this is simulated at different angular resolution. So as it would look like, of course, this doesn't take into account change of frequencies and so on, but only from the point of view of pixel size, how it would look like by when observed by Euclid, then the original HST, then Keck adaptive optics, and then any very, very high resolution case that kind of tends to the radio problem. So now the idea is how to improve the lensing constraint. We need more lenses. We need not many more lenses, but a few lenses observed at higher resolution. And then how many do we need to actually distinguish CDM from alternative models? So to show you how this works, so there's different things you can do. So the first one is to make mock data of how the same lens observed with the same instrument would look like a higher signal to noise. So these are sensitivity maps for the same HST lens, but observed for more orbits, this under the assumption that this will directly correspond to an increase in signals to noise ratio. So the images all look the same with less noise in practice. And then what you want to keep in mind here is that the colors, so darker colors, are the best because they are at the small masses, and they allow us to go down in mass and distinguish different models. So clearly, increasing signal to noise in the data, signal to noise ratio in the data is a good thing, because the dark area now extends not only exactly where the brightest peaks are, but along the entire arc. And it's bigger, and so this means that there's a higher chance of detecting substructure even far from the lensed arcs when the noise is lower. So in practice, from these maps, then we calculate what's a distribution of masses that, with this kind of observation, one could hope to detect, and this is how it looks like. So more orbits mean that we can go a bit more down in mass, but also that since the total area is larger, that we can detect more. And so the peak moves and the area of the curve moves. Another technique can be to increase the resolution. So here, this is what will happen if the same lens at HST will be observed in adaptive optics, in this case by Keck. And here it's a similar effect. So we have a larger area when we can detect very small halos, but most importantly in this case, thanks to the increasing resolution. So here you can see that the histograms, the peak moves, but the low end is not so different from one case to the other. While here, the area at low mass is really, really different. And so this is actually what could make a big difference between the two cases. And finally, to show how the effect of the source is like, this is the same mock image. It's the same system where I have used the same lens model, but changed the source. So on the left is the original one. And then on the right is 3 cases where the source is made by a double Gaussian distribution, a larger Gaussian, a 2D Gaussian distribution, and then an elliptical galaxy, a spiral galaxy taken from HST data and put at high redshift. And you can see that the details here are not important, but that you can see that all these maps on the rightmost panels, then they all look different. So this is all very tricky, and unfortunately we need to go through this process for each lens to have reliable prediction. So now that we've seen all these images and summary of what it actually means, so here both plots show for different cases the number of lenses on the x-axis that you need to detect a certain number of halos, which is on the y-axis. So of course, more lenses mean more detections. What we have at the moment is something like 20 lenses at one orbit, 20, 30 lenses at one orbit. And so where we detected one substructure, so this is consistent with this CDM prediction because the error bar, so 1 plus minus 1 doesn't tell us much. But we can see that if we had the same number of lenses, like even 20 or 30 observed with 4 orbits or 10 orbits, or at higher resolution, or with ALMA, then the 1 sigma regions would move away from 0, from 1. And so this would allow us to test CDM. So the idea here, in this table, where I'm showing like probability number of lenses that you need to exclude CDM. So what if we keep detecting nothing? At how many lenses can we really be sure that CDM at this point is disfavored? So with at different levels of probability. So if one really wanted to be sure, and then said what the probability of CDM is 10 to the minus 4, then one would need many lenses, like 70 lenses of the current resolution that we have, but not so many if we were able to increase the number of orbits. Of course, it also means increasing the number of time and proposals, etc., etc. But so this is a way of doing this. And using higher resolution and extending the observed time to reach a higher signal to noise ratio in the end give similar results. So these are both two viable strategies that we should try. So more in practice, going back to this plot. So these are the constraints that we have now combining the two samples. So this yellow line is what we have now combined the low and high redshift systems. So these are all HST systems with observation of one orbit. Then if we had the same numbers of lenses, but observed for 10 orbits or at higher resolution, so with Keck adaptive optic, for example, you see that these 95% confidence limits move to the left and starts to get closer with what actually is the measurements from the Lyman alpha forks, for example. So this is for something like 30 lenses. If we had ideally 80 or 100 lenses, then of course we will move even to the left, and this is what will happen. So here I go back. So now here you can notice that unfortunately they don't move so much, and the yellow line also almost doesn't move because at some point you reach a limit of what your resolution can tell you. So we really need, this is why we need higher resolution data to go at lower masses. So the hope is that this will be possible, and then the nice thing of all these methods is that they probe the same problems. So it's the nature of dark matter on different scales. They're independent, they suffer from different systematics, and so if they all start to give the same results, then it would be really exciting. So at the present time, so CDM is still fine. We have excluded very warm models, so kilo electron volt masses below, depending on which papers you read, below 5 kilo electron volt. And so depending on what the future observation will tell us, we will keep pushing this towards higher masses, and so excluding warm dark matter and keeping CDM, or some constraints can come in from the left and restrict the range. So this is about optical data. And now I finally have an example of what, so hopefully the future looks like. So these are images from a paper that is in preparation. These are radio data from the global VLBI network. So this huge network of radio telescope all around Earth. And so you can see here that the images are incredibly tiny. And here on the right, in the top right, you have the source. So we can actually see the radio jet at an incredibly high resolution. And the white contours show where the optical emission from Keck adaptive optical observation is. And so you can see that the two instruments would give different shape of the lens images, but that these radio data are really high, really nice. And so what is ongoing now is going past this smooth model and try to induce perturbations into these images to see if we actually see some substructure. Because, as I said, these thin arcs, if you put something on top of them that's massive enough, you should see a perturbation. For instance, there is a case that hasn't been analyzed yet. It's another lens, but always from the global VLBI observations. And if you zoom into the arc, you see that there is a gap in one of the images, and we don't know yet if this comes from the fact that the two images are merging at that point, or that there is something on top of it that blocks out the light and creates a deflection. So this is what is the hope for future observation on very small scales. And then I will have like a 5 minutes parenthesis on larger scales. So this, I told you so far, is mainly to distinguish CDM from alternative warm dark matter models. Self-interacting dark matter can also produce similar effects, but the model that strongly suppress the number of substructure have been ruled out by other probes. And so for self-interacting dark matter, we're using a different point of view. So on the top right, you see predictions from dark matter only self-interacting dark matter simulation. So this looks like the plots before with the number of halos, but these are actually density profiles. So the white one is the halo in cold dark matter, and the other ones are stronger and stronger self-interacting models. So due to this interaction at the center of halos, energy and momentum is exchanged, and so you can imagine in the highest density region, particles move in an isotropic way, and then the central peak is actually smoothed out, and you get a core. All this prediction has relied so far on dark matter only simulation. So there's no central galaxy. Dark matter is the only thing that happened. But of course, we know from CDM already and hydro simulation that baryons are important, that they can modify the properties of halos and galaxies. And so we've started to run zoom-in simulations of elliptical galaxies that resemble the properties of lenses that now include baryons. And not surprisingly, the baryons change the prediction from that for dark matter only simulation. So we have simulated a sample of 10 early type galaxies from the illustrious simulation, are redshift 0.2 and 0.5 with CDM and baryons and with SIDM and baryons. So in this case, it's a self-interacting dark matter model with a cross-section of 1, for those of you who know what this means. So it's self-interacting, but not incredibly self-interacting. So it doesn't really affect the number of structures, but it affects the profile at the center of halos. And what I found is that the halos that we simulated can be actually divided in two. So the most massive lenses that here on the, again, stellar mass versus effective radius have stellar masses above 10 to the 11 solar masses. These form quite recently, and they form a core. So in self-interacting dark matter, the central distribution of dark matter is way lower than in CDM. This goes accordingly to predictions. However, this is not true at all masses. So for lower masses, where the stellar mass is around or below 10 to the 11 solar masses, and the galaxy is more compact, this is not true. And actually, the opposite happens in SIDM. There's this interplay between SIDM and the baryons that create profiles that are denser than in SIDM. So this is a small sample, but it shows that dark material predictions are not reliable. And of course, these results also could be influenced by what is the hydrodynamical model in the simulations. But nevertheless, they can have an impact. And so from the lensing point of view, so lensing is affected by mass and distribution of mass. So a more chord profile is less lensing effective than a Caspi profile. So this means that for the first category of objects, these are again mock images. In CDM, their strong lensing effect is stronger. So the Einstein radius, so the size of the lensing images is bigger, and in SIDM is smaller. And for the second category, it's not so clear. So the sizes are the same or even bigger in SIDM. And of course, this can influence the distribution of Einstein radius that will be observed by surveys, for example. So when Euclid will come and will put out thousands and thousands of lens systems, then we'll be able to have a huge statistics of sizes of lenses. And depending on what is the model that we believe is true, this could look different. So from our simulations, at least, there is a clear difference in the distribution of Einstein radii in CDM and in SIDM for this population of galaxies around 10 to the 13 solar masses. And I just want to finish to mention that this is our ongoing work, because the simulations were new. So then it was it's a small sample. We are extending this sample by using an actual SIDM box of 50 megaparsec. And with a larger statistics, we see that things might not be so clear. And actually, the difference between SIDM and CDM on average are almost erased by the presence of baryons from the point of view of lensing. This is a paper that's been written by a student that Claudio Mastromarino was a student in Bologna and just graduated. So from the lensing point of view, this is exciting. And then searching for, again, another analog to see the same thing. So SIDM is predicted to have an impact on the profiles. But given this isotropic exchange of energy and momentum of the center, this also affects the shape of the halo, the shape of the galaxy. And this is something that can be observed. This is another work in preparation. This is something that has been observed in X-ray for elliptical galaxies. So this on the bottom left, these are images of elliptical galaxies by Chandra and XMM that have been published recently, and one can look at the distribution of the X-ray emission. They measure the X-ray isotops, and then under the approximation, the gases in isotropic equilibrium with the dark matter measure the shape. So we have this real data. We're trying to do the same with these 10 simulations that I just talked about, and try to combine this with the lensing measurement to see if it's really true that once we include the baryons, the difference between CDM and self-interacting dark matter at the very center of elliptical galaxies almost vanishes, and as a consequence, if all the self-interacting dark matter constraints should be revisited. And this is kind of exciting because all the progress in CDM hydro simulation that include the baryons are now trickling down to the rest of the models, even those lower. But hopefully there will be exciting results in the future. So yeah, this is my summary. I don't like text summary, so this is a visual summary on what is important for dark matter and alternative models of dark matter in combination with lensing. So on the very, very small scales, we're looking at the mass function of halos and subhalos at low masses, and we're trying to distinguish CDM from warm dark matter models by counting how many perturbations we have. And data will improve when more ALMA and radio and ELT observations come. And so we'll be able to probe this region where the differences between the model are so big that it should be possible to distinguish between them. And on the other hand, with the size of lensing distribution of mass and their shape, we're trying to say something between something about the difference between cold and self-interacting dark matter models. And I hope this all makes sense. And yeah, thanks for listening to my talk.
Thank you.